Here we get to the real meat of slope, rate of change, and slope-intercept form of the equation. What we're trying to do is take this theoretical equation like this right here and relate it to the rate of change equation here. So if you remember that our function values at x is the same as y. And so if you'll notice here, when we have points of the form x1, y1, or the form x2, y2, that when we're creating our slope formula, it's the same thing as saying we have our x1 and then our function value of x1, and then we have our x2 and our function value of x2. So it's the same item, it's just using the function value instead of y. So again, y1, f of x, y1, f of x1, excuse me, so we have y1 here and f of x1 here. And then on the same point, we have y2 and f of x2, and the same thing, y2 and f of x2. So this is the same thing, just using the idea of function values rather than just the y to represent the values in the slope-intercept form of the equation. So then we're looking at these applications, and we're relating again two sets of numbers. We're relating our domain, which if you remember is our independent values, and then our range, which is our dependent values. And then we're trying to find out which values apply to each. So in this case, we have the population of men start living in a city in two different times. And we're trying to figure out, again, we have population, we have year or time, and we're trying to see, again, which one. Does the year depend on the population? Does the population depend on the year? And arguments can be made for both, but typically time just goes on continuously, and it doesn't depend. Like if all of a sudden we change the population of men, if we have a sharp decline or a sharp increase, there's not going to be, time is not going to change in that regard. And for most of the time, our year, our time is going to be our independent value, and our population is going to be our dependent value. So this is our men population. So now I know that when I have this, we have the fact that my year is going to be my independent, which is also going to be my x. And then my dependent is going to be the population, which is also going to be my y. So then we're going to extract these two situations. So when we're calculating the rate of change, we're going to calculate the change between two certain situations. So we had the population at 2000, and then we also had the population at 2013, which is again that other dependent value. So what we can do is we can set up our function values, or our points, if you will. So we had a function of x. So the population function at the year 2000 is equal to 11.2 million. The function value at 2013 is going to be 15 million. And again, this is my x in the pink, and the yellow is going to be my y. So let's put it into our rate of change equation here. So we can make this one x1, f of x1. We can make this x2, f of x2. So as we look at this, my rate of change formula is equal to f of x2 minus f of x1 all over x2 minus x1. So subtracting these two values, oops, that needs another zero. Subtracting the values on top and subtracting on the values on the bottom, we get a change in 3.9 over 13. But let's not forget what these values stood for. Remember, our f of x values is our population in millions, and then the value on the bottom is years. So what we're saying is that we have a change of 3.9 million over 13 years, and this is positive, so it's going to be an increase. And of course, that's illustrated by here. I went from 11.2 up to 15 million. So that is 3.9 million per 13 years. Or if we divide it out for that unit rate, we get 0.3 million in the population over every 1 year, just dividing it out. So when it's saying create the ordered pairs, so we did, and if we, again, we can create it just to be the 2000, comma 11.2, and we can create this one to be 2013, comma 15. And then we found the slope. So the slope is 0.3 million per year. So that is what the slope means. So not only creating your x and your f of x values, but also remembering what the label is on this will help you define what the rate of change is for your situation. So look at the next one. We're going to again look at, we have, we're looking for our independent, we're looking for our dependent. Remember, that is our x, and I said y, but that is our f of x values. And then we have two items. We have our x, our time, and then we have the amount of active duty service members who was discharged. And then we have this value, and then we have this active service duty members discharged. So the x is going to be our time. Again, time is, a lot of the time is independent. And then our dependent value, well, depending on the year, we can estimate with our modeling, we can estimate what the service members discharged was going to be. So again, creating this value, we have f of x1 is equal to y. We have f of x2 is equal to y. But again, where our values are going to be the ordered pairs. So in 1994, our time, there was 617 service members discharged. And in 1998, oops, the number went up to 1,163. And again, x1, f of x1, x2, f of x2. So we're putting these values in, and this gets very theoretical. So let's put these values in, and we can say that the f of x2 minus f of x1 all over x1 minus x2. So subtracting these values, we get 546 over 4. So what we have to do again is remember what these values are. Remember, this is our f of x values on top, and this is our x values on top, on the bottom. And f of x represented 546 service members discharged over that 4 years. Never forget what these labels are, and it gives that context a lot better. So when we divide that out, dividing it by 4, that means that they increased the number of service members discharged by 136.5 every year, approximately. So we have context. We can also find these values in simple function values here. So again, remember, we need the point x1, f of x1. And we need the other function value, x2, f of x2. And we're putting these values in. So when x is 1, I say x1 is equal to 2, f of 2, well, in our function equation, we have that that's 2 cubed. So my first point is when f is 2, when x is 2, f of x is going to be 8. Doing the same thing for 4. x2 is 4, so f of 4, raising it to the third power according to that function value, is 4 to the third. So my second point is 4, comma, 64. 4 to the third. Remember, 4 times 4 times 4. So then we can find the rate of change doing that same equation. And solving. So this is the function values here, and then the rate of change is 28, or 28 over 1. I'm going to pause the video and then put find the function values, your points, and then calculate the rate of change. So continuing to put the function values in for -1 and 3, we find the 2 points are going to be -1, -4, and 3, 12. And using our slope equation, we find that our slope or our rate of change is 4, which you might have noticed is exactly the slope of this linear equation. So we went a long way around the barn, but just to show that again, it shows the same type of thing. Our slope, our rate of change are related, and we can use these when we're applying them to other application situations.